In this lesson, using the example of a very famous mathematical sequence named Fibonacci sequence, we will explain why writing a recursive program may sometimes be very intuitive and simple, but it may not be the best thing to do. And the prerequisite for this lesson is that you should know about functions, and you should also know about the concept of recursion in programming. Now, Fibonacci sequence is defined by this particular recurrence relation. The first two elements in this sequence are 0 and 1, and all other elements are the sum of previous two elements. So the third element is 1 plus 0, which is 1, and then we go like 1 plus 1 2, 2 plus 1 3, and so on. So we can also say that this is f0 and this is f1, and f0 and f1 are calculated by this condition, and f2 onwards we calculate them by this particular recurrence relation. Now, Albert and Pinto are two students of my code school, and they have both written programs to find out nth element in the sequence, and they have both written two different solutions, and let us see what these two different solutions are. Albert writes a method fib that takes n as input and gives fn in this above sequence, and the program goes like, if n is less than or equal to 1, return n, else we will initialize two variables f1 to 0 and f2 to 1 and run a loop from 2 to n where I'll have a variable f that will calculate the sum of f1 and f2. f1 and f2 at any point in this loop will have the, or rather store the values of the previous two elements, and f at any stage in this loop will have the current element. Now we need to update f1 and f2, so f1 now will be f2 and f2 now will be f, and finally when we come out of this loop we can return f, and this gives us the pseudocode for Albert's implementation. Now Pinto also writes a method fib of n, but Pinto has recently learned recursion, and he says that hey, there is a lot more simpler method to solve this problem. So his program also goes like, if n is less than or equal to 1, return n, but else return fib of n minus 1 plus fib of n minus 2. So he writes a recursion, and this particular condition, if n is less than or equal to 1, is the base condition or the termination condition, so that the recursion does not go on endlessly. Now let us quickly try to write these programs in an actual compiler and see what happens. So I will write a C++ program, and this is the Visual Studio compiler open in front of you. So this is Albert's code, where he has written an iterative program where he is iterating through all fi's in a loop from 2 to n, and I'll come to the main method and have a variable n, and I'll ask the user to input an n. So I'll say, hey, give me an n, and I'll input this. I'll also have a variable result that will store the return from the function once we pass n, and I'll simply print the result. Now let us quickly run this program and see what happens. Now this says give me an n. Let's say I give n is equal to 6, and the output is 8, which is correct. Now I will run this again, and this time for an input 40, and this time the output is 102334155, which is a 9-digit number. Now let us write Pinto's implementation, and this time I'll modify this method. So I'll say that if n is less than or equal to 1, return n, else return fib of n minus 1 plus fib of n minus 2. And we could also write an else here, but that would be redundant. So let's run this and see what happens. So this time again, let's say we give the input 6 first, and this gives me 8, which is correct. And let's give n is equal to 40 again, and this is not finished yet, this is still executing, and I'm waiting, and this is still executing, and boom, it finally comes. So this gives me the correct result, but this time it takes a couple of seconds to give me the result. And why is it so? I thought recursion is good. Let us see. Now Albert has written an iterative program and Pinto has written a recursive program. So what happens with Albert is that to calculate fn, he already has f0 and f1. So to calculate fn, he goes on to calculate f2 from f0 and f1, and then he goes on to calculate f3 from f2 and f1, and he goes on till f of n. So he calculates each of these f2, f3 and fn exactly once. So for example, if he wants to calculate f5, he goes on building it like from f0 he goes to, sorry, he already has these two values f0 and f1. From here he goes to f2 and then to f3, f4 all the way till f5. Now if Pinto has to calculate f5, he makes a recursive call to f4 and f3. So I'll go in order in which the functions are called in an actual program, and I'm using f4, f5, all these names as shortcut for fib of 5 and fib of 4. So now f4 recursively calls f3, f3 recursively calls f2, and f2 recursively calls f1. f2 also calls f0. Now f0 and f1 do not make any further recursive call. They simply return 1 and 0 respectively. So this also makes a call to f1, and we keep on drawing this structure. Now f5 also calls f3. Now this particular structure that we have drawn here is called a recursion tree. Now we can see here that the value f2 is actually being calculated thrice, and similarly f3 is being calculated twice, which is an unnecessary overhead or unnecessary redundancy. So in the left, or the iterative program, while we are calculating each state or each value of fi exactly once, in the recursive implementation we are calculating it multiple times. For example, if n is equal to 5, we are calculating f2 thrice. When n is equal to 6, we are calculating f2 5 times. When n is equal to 8, we calculate f3 13 times. And if n is equal to 40 that we had used in our example, this number is 63245986, which is crazy. And similarly, like f2, f3, f4 and fi for any general I is being calculated a number of times. So the running time of this program is growing exponentially as the input increases. And you can also write a simple program to find out how many times f2 is being calculated or any other fi is being calculated. So as we can see from this example, recursion can sometimes be very simple and intuitive to write, but it could be expensive in terms of time and space that it takes. In another lesson, we will see how to analyze the time complexity of a recursive program. In yet another lesson, we will also see that how to avoid this overhead of calculating the same state again and again by using a technique called recursion with memoization. So thanks for watching.